Good morning, class. We're looking at section 3.4, the chain rule. So we covered derivatives of polynomial and exponential functions. We moved on to the product and quotient rules, derivative of trig functions, and now the chain rule. So first, I want to again quickly recap what we have here, and then the new stuff. As you can see, on the left side are the formulas that you have learned, okay? From the constant to the power rule to the exponential to this, trig functions, okay? Those are the definitions. This is the limits we looked at. The limit of sine theta over theta is 1. Limit of cosine theta minus 1 over theta is 0. In both cases, as theta approaches 0. We looked at the product rule. Fg prime is f prime g plus g prime f, and the quotient rule, f over g prime is f prime g minus g prime f over g squared. Now we are adding the chain rule. The chain rule has got to do with the composite function of f of g of x. By definition, f of g means that, and if we want to differentiate that, we differentiate the outer piece, the shell f, we get f prime of g of x, and by the chain rule, we tag along the derivative of the inner piece, g prime of x. And in this format, this is in Leibniz notation. dy dx is dy du dx, and it becomes clear as to what we mean by that in a moment. First, just to refresh your memory about composite function and what f of g means. F of g means f of g of x. So if I have f of x as x cubed and g of x as 1 plus x squared, f of g means this x must be replaced by the g function, which is 1 plus x squared. Okay, so f of 1 plus x squared. So you put it in and you get 1 plus x squared to the third power. Very straightforward, very simple. I hope everybody remembers this. Now, when we calculate the g of f, okay, now this x must be replaced by f. The f function is x cubed. So we write it in this fashion. So g of x cubed. So replace, and you end up with this. Now, this one you have to change x cubed to the second power using the power rule, and becomes x to the power of 6. Whereas f of g, you can leave it like that. And obviously, as you can see, f of g is not equal to g of f. All right. Now, the only thing I want to add, generally speaking, f of g is not equal to g of f. Anybody remembers when they become equal? When is it that f of g equals g of f? Anyone remembers that? If two functions are inverse of each other. F of f inverse equals f inverse of f equals x. The only time two functions have the same composite function, f of g and g of f, if f and g are inverse functions. Okay, so f of f inverse o f is equal to x. All right. Why do we need the chain rule? Okay, so we can handle examples such as the square root of 10x plus 5, or examples such as 10x squared minus 1 to the power of 50. Okay, in which case, here's the chain rule. If g is differentiable at x and f is differentiable at g, or g of x, then the composite function f of g of x is differentiable at x. So what is the derivative of f of g of x? The outer piece, the shell, is f, so take the derivative of f prime evaluated as at the inner piece g of x. By the chain rule times the derivative of inside, which is g prime, if we use in Leibniz notation, if we use his notation, where y is f of u, that means function of the variable u, and u itself is a function of x, then the y dx is equal to the product of the y du dx, where du and du, if you treat this as a fraction, and really we shouldn't, they cancel each other, class notice, and you get the same thing back, dy dx. Again, we look at a couple of examples to make some sense out of this. Therefore, we have this idea of a power rule. I want to discuss that. Everybody remembers the derivative of x to the power of n is n x to the power of n minus 1. Now, instead of x, let's change it to a function g of x. So the first portion is the same, n x to the power of n minus 1. This one is n x to the power, g of x to the power of n minus 1. Okay. Now, what changes? Okay. If you look at this one, the base is x, and everybody, what is the derivative of x? 1. Do we have to write it? It makes no difference. But what is the derivative of g of x? Is g prime of x. Should we write it? Yes, it does make a difference. That is one way to remember the concept. Okay, so g prime of x. The bottom one is known as the general power rule or the extended power rule. Okay. And again, I'm repeating the same thing, class. The derivative of the composite function, this is one way to write it. And that's precisely the same thing that we had here. There is really nothing brand new. Now, before we look at examples, I thought a set like this would really help understand the concept. And the way you differentiate it, if you pay attention to what I'm going to tell you, it becomes very easy. So the first one, if I'm differentiating this, I'm going to read sine. Take a look. I'm going to read it as sine, and I'm going to pause. Okay, I want to show you this. I'm going to pause. Sine, that's the shell, that's the outer function. So what is the derivative of sine? Cosine. Okay. So sine, the derivative is cosine. Now, the argument is 2x, so I'm going to write it. Let me just actually use it. The argument is 2x, so I'm going to write it. So far, nothing new. Sine, the derivative is cosine. Now, what is the derivative of 2x? Because it is no longer x, it's 2. So you write that, and of course you bring the 2 in front. So I hope you see how this one is done. I'm looking at the second one, and again, I read the same thing. Sine, and I'm going to stop. I'm going to pause, and I'm going to say sine. The answer is cosine. Sine of what? X squared? So cosine of x squared. But what is the derivative of x squared? 2x. And I put the 2x in front. Now, the only thing I want you to pay attention to, the next one is slightly different in that I'm going to rewrite this. So I want you to notice that this means, and you don't have to, as long as you recognize the meaning, it's fine. It means sine x to the second power. In other words, something to the second power. And therefore, you use the extended power rule. So we're going to use this, everybody. The extended power rule. N, which is 2. G, which is sine to the power of n minus 1, which is 2 minus 1 over 1, times g prime, the derivative of sine, which is cosine. So I hope you see the answer 2 sine x cosine x. And needless to say, this is sine of 2x. You don't have to worry about that. That's the same as sine 2x. All right. So I think this is a very good example to give us really the essence of this chain. Okay. Here's what we are given, everybody. We are given y as a function of u. We call it f of u. Y is u to the power of y. Okay. Then u itself is a function of x. We call it g of x, 10x cubed plus 2. So we want to differentiate this, and we're going to look at it from the point of view of Leibniz and then the composite function that was mentioned. So let's look at it both ways. The reason I want to do that because sometimes one is easier than the other class. You really have to expose to both. You have to know both, and you have to know how to use them because definitely one is easier than the other in some cases. You need to understand what that means. Start with dy dx is dy du. Start with dy du. So take a look at it. Dy du, everybody. Y is u to the power of 5. When we say dy du, we mean differentiated with respect to u. So can anybody tell me what's dy du? Class, what is dy du? Differentiate the y with respect to u. The u is the independent variable for y. So what is dy du? Anyone? Houston, we got a problem. What is the derivative of x to the power of 5, class? Anybody want to help us with that? What is the derivative of x to the power of 5? Okay, it's 5x to the power of 4. So this is 5u to the power of 4. Then du dx, here's u, du dx. That means differentiate this piece. And that's 30x squared. You're done with the differentiation. What do you do next? You are simplifying it by putting them together in this fashion, replacing the u with 10x cubed plus 2, and finally 150x squared times 10x cubed plus 2 to the power of 4. So this is your calculus step. Then you replace the u, and then 5 times 30x squared sits in front. So this is using this notation in Leibniz notation, and it was easy to do. However, we can easily find their composite function first. So what is FOG? FOG, FOG, f of u is u to the power of 5. Replace the u with 10x cubed plus 2, and it becomes 10x cubed plus 2 to the power of 5. And now differentiating this again. So what is this? Something, this is the inner piece, is being raised to the power of 5. This is the extended power rule, everybody. So n sits in front, same parenthesis to the power of 5 minus 1 over 4 by the chain rule times g prime times the derivative of 10x cubed plus 2, which is 30x squared. So f prime of g of x, f prime of g of x, it's 5 times 10x cubed plus 2 to the power of 4. G prime of x is 30x squared. Okay, in other words, it's important to realize this function is g of x, okay, in essence, okay, and that's giving rise to g prime, okay. Now, if you rewrite it, you have the same answer as the previous part. Which one is easier? You make a decision, but more importantly, you gotta be comfortable with the concept, class, okay. As you see in this example, either way can be done. In some cases, finding the composite function itself takes so long that it's not worth it, and we stick with the Leibniz notation. So that's why you want to learn both, okay? We're going to write the composite function f of g, and again, you don't have to do it this way, again, just for practice, where y is sine of cosine t, and we want to go with the notation, again, with Leibniz notation. Again, I wouldn't do that. I'm just, if I'm asked to differentiate this, I wouldn't go this route. But just to give you an idea, what you want to see is that what is the outer piece? Sine. Never mind what's in there. Let me put the, so never mind what this is. Sine, that's your outer function. That's the shell function, sine. Okay. And your inner function, okay, so this is sine, if you will, of u, where u or g of x is cotangent x. Okay, so I hope you see that. Sine of, this is the inner function, u or g of x, and then sine is the shell. Okay. Going through the process of dy du. Okay, let's start with this, dy du. What is the derivative of sine? Cosine u. That's dy du, that's done. Times du dx, that means what is the derivative of this guy? Cotangent, okay? And that's negative cosecant squared. So you put them together. And you change the u to cotangent, you bring the negative sign in front. That's the final answer. Now, if I was going to do it by the method that I did in the very first example, I would do this, class. I would say, if I'm differentiating, I say y prime equals, okay, I'm going to read this sine and I'm going to pause, sine, the derivative is cosine. Okay, but remember, it does have an argument. So what is the argument? You can't have just cosine without anything. So sine, the argument is cotangent. So cosine, the argument is cotangent. Times. Now, what is the derivative of inside cotangent x? I would go this route, coming up with the same answer, okay? But it's absolutely up to you. Composite functions and their derivatives we are going to discuss. Let's look at a bunch of examples to make some sense out of this. Starting with a very simple example, and pay attention to the first one that uses the extended power rule. So something, never mind what's in there, you can ignore it. Something to the power of 50. So what is the derivative? 50 sits in front, becomes the coefficient. The exponent goes down by 1, becomes 49. And then last step, you need the derivative of inside. The derivative of the parentheses is 20x. You're done with calculus. You put the 50 and 20x together, we get 1000x. It's extremely simple, class. If you just, pay attention to the steps, it works out easily, I promise you. What is your first step here? Y equals square root of 10x plus 5. What should we do first so that we can differentiate this easily? Anyone? Step 1, algebra.
Professor, would we get rid of the square root?
Beautiful, beautiful. 10x plus 5 to the power of 1/2. We do exactly the same thing that we did before, okay? It really makes no difference. So what we have learned before, it's gonna stick around. So what happens next? Same thing. Power rule now is the extended power. 1/2 sits in front, becomes the coefficient. And then you subtract 1 from it, 1/2 minus 1 becomes -1/2. Now we need the derivative of the inside, 10x plus 5. The derivative is 10. So take a look. 1/2 sits in front. The exponent, you're going to write it 1/2 minus 1 becomes -1/2. And then 10x plus 5 gives us 2. Done with calculus, we're going to rewrite this. Okay, everybody? We are going to rewrite this. How? Well, 1/2 times 10, the product is 5. And this -1/2, you take it down, you make it +1/2, the exponent. +1/2 is what? The square root. So take it down, make it +1/2, change it to a square root. All right. Pretty straightforward, class. All right. What about this one? Number 5 is a multiplier, and it's going to, keep on being a multiplier. Nothing changes. So y prime. 5 remains. It doesn't go away. Okay. Now deal with this. Now this is a simple case of a power rule. So 5, and then this 4 becomes a coefficient times 4. 3x minus 2 to the power of, you're going to subtract 1, you get 4 minus 1, 3. And this one is not x, it's a function of x. That's why you tag along g prime of x. So times 3. You multiply 5 and 4 and 3, and you get 60, and you are done. Okay. What happens next? You're dealing with a bunch of exponentials. Okay. In general, remember the derivative of any exponential is itself, and then we may have to do something else. For example, the derivative of e to the power of x, we know it's e to the power of x. But what happens here if it's e to the power of kx, everybody? Well, look at the exponent. The exponent is your g of x. When you differentiate it, you get k, so you put the k in front. But if it's e to the power of g of x, then the derivative of g of x, or g prime of x, sits in front or just in the back, and then we bring it up. So let me show you how I will deal with that so we can see this. If I'm given this class, I'm going to write y prime. I see exponential, I say the answer is itself. Right away, I just write it. Okay. So I say it's e to the power of 10x. The answer is e to the power of 10x. However, the exponent is not x, is 10x. What is the derivative of 10x? 10. I write it this way, and then I put the 10 in front. Okay, everybody? What if I'm dealing with this guy? I'm going to write y prime is itself. First, I'm going to say the answer is itself. Then I look at the exponent, and I see the exponent is t squared, not t. So I need the derivative of t squared. I put next to it, and then I rewrite it. Okay, so I hope everybody is comfortable with the concept. Okay, class? It's very straightforward, and it's really not that big of a deal. Okay. When I do number 5, really there are a couple of different ways. I'm going to show you the easiest way, and then you take it from there. If you want to do it a second method, I leave it up to you. First and foremost, I notice I can rewrite this as e to the power of 2t because of the power rule, t times 2. And now it's a simple differentiation. The answer is itself, e to the power of 2t times 2 times 2. Now it becomes an easy case. We don't worry about it at all. I hope everybody is comfortable with that, okay? So exponentials. All right, we are differentiating this. We are combining a product rule and a chain rule. Before we do that, I want to explain something about this number 5 sitting in front class. If number 5, and this, since it's fairly small number, you can say 5x is your first function, and then 3x minus 2 to the power of 4 is your second function. So this is the product of 5x and the rest of it. Okay. However, if instead of 5 you have an involved number such as 5,000, 10,000, or 0.21 or 2/3, you don't want to get that involved. If that happens, I recommend you do this. 5 is a multiplier, or 5,000 or 10,000 or the number, keep it out as a multiplier. So that one multiplied by everything that you do. And now you have x and then 3x minus 2 to the power of 4. Okay, class? Again, if number 5 is involved, this is what you do. Okay? Trust me, it makes life easier that way. You can do it right here too, but either way is fine. So you can look at it from the point of view of two pieces. 5x is one piece, and the parentheses to the power of 4 is the second piece. All right, product rule f prime g plus g prime f. The derivative of 5x is 5 times the second piece. Plus, what is the derivative of the second piece? We've done this many times. 4, in fact, in the previous page was that 4 times 3x minus 2 to the power of 3 times 3 by the chain rule, and now by the product rule times 5x. Okay. Now this is by the product rule class, this part of it. Now it's not a matter of factoring. There are two ways to do it. You can just factor it just the way it is. Okay, everybody, we can do that. Or you can simplify the second part, 4 and 3 and 5x, okay? You put it in front and put it as 60x and then factor. What's in common? 5 is in common. I'm looking at number 60 and number 5. 5 is in common. Plus number 5, number 60. 5 is in common. 3x minus 2 is in common. But what is the exponent? The exponent is 4 here. The exponent is 3 here. So you choose 3x minus 2 to the power of 3. Okay. So what happens is we write 5 we write 3x minus 2, and we choose the smaller of the two exponents. Now, if you look at the first one, class, this piece, what is left of it? What about the green piece? What is left of the green piece? Okay, you have 3x minus 2 cubed gone. The only thing left is 60x divided by 5. 12x. I'm assuming everybody is very comfortable with factoring, and practically we are done. Or if we go this route, if we use without the green one, okay, that's why I put them in blue. Those are the ones that are left. And however you look at it, 12x and 3x, they add up to 15x, and you're done. So a big chunk of the work is what? Factoring. Here's the next one, number 7. Anytime you have a numerator which is a number, just a number, 1, 5, or 10,000, doesn't matter. You don't have to use the quotient rule. It is easier to do what we did before. We rewrite this such that the power rule, in this case, the extended power rule, can be used. So now this is a very simple case. -4 sits in front. Then you subtract 1 from -4 becomes -5. So the same parentheses to the power of -5. Finally, the derivative of the parentheses, g prime of x, the derivative of this, which is 14x minus 1. You're practically done. The only change you have to make this -5, take it down, and make it positive exponent. Take it down and make this -5 positive 5. That is your algebraic step to finish the job. However, if you're looking at the next one, you should use the quotient rule. So I want you to distinguish between 7 and 8. 7, the numerator is a number. Again, could we have done the quotient rule on number 7? Yes, but you really don't want to do that. Why not? Because it's easier and faster using the extended power. All right, now we're going to use the combination of the quotient rule and a chain rule. How? Let's see. F prime g minus g prime f over g squared. The derivative of the top is 1 times the bottom minus. Now here's the chain rule. The bottom needs a chain rule. What is the derivative of that? 4 times 2x minus 1 cubed times the derivative of the inside, which is 2, and then times the top x. That's the numerator. What is the denominator? Just write the same thing to the power of 2, meaning just exponent 4 becomes 8. So multiply the exponent by 2, that's all. If you see a case like that, the denominator has an exponent, just multiply it by 2. That's how you square it. We're done with calculus. We are going to rewrite this, okay, algebraically to finish the job. Okay, notice 2x minus 1 is in common. Okay, what exponent do we use? This is number 4, and this has number 3. We use number 3, the smaller of the two. So if I use number 3 from the first piece, 2x minus 1, one of them is left. Okay, I write that. Over here, 2x minus 1 cubed is completely gone. So what is left? Minus 4 and 2x, the product is minus 8x. So this is factoring. All right. Again, we had one step of calculus. We were done. Now we are doing a lot of algebra. What is the next step? Notice 2x minus 1 cubed, 2x minus 1 to the power of 8. This goes away, and this exponent changes to 5. That's the first thing. Then we write it. The denominator is x minus 1 to the power of 5. What about the numerator? Brackets, add them up, 2x and negative 8x. They add up to negative 6x. And don't forget, there is a negative 1 there. And it's really that simple, class, okay? So I hope everybody is paying attention to that. It's really not a big deal. And we are ready for the next example. Okay, class? next example, I hope. All right, so how do we do this? Again, because the numerator is a number, I wouldn't use the quotient rule. It's easier to rewrite it. Here's the algebraic technique we are going to use. Algebraic technique we are going to use. Okay. And so what happens? Becomes an easy case of an extended power rule. 4, it's going to be there, so we're going to keep it. So 4 times negative 1/2 becomes a coefficient, so 4 times negative 1/2. Same thing, whatever is in the parentheses, to the power of what? Subtract 1, negative 1/2 minus 1, okay, which is negative 3/2, by the chain rule times the derivative of the inside, which is 2x. You're done. You are going to rewrite this class, okay? You are going to rewrite this. Okay. You are going to rewrite this. And it's an easy, one to do, okay? Let's see what happens. You have 4 and negative 1/2 and 2x, okay? 4 times negative 1/2 times 2x. This negative 1/2 and 2 cancel each other, negative 1, negative 4x comes, and we write it in this fashion. Now, all you have to do, this negative 3/2 exponent, you want to get rid of it. How? Take it down, make it positive. Take it down, make it positive. Now, if you didn't write it in this fashion, for example, if you wrote this as minus 4x over x squared plus 3 to the power of 3/2, it's fine, but you're a calculus student, you should have no problem changing this to this format, okay? Fractional exponent to a root function, so that shouldn't be any problem. Okay. Now, combination of the chain rule and the quotient rule. The first thing we want to do, class, we want to ignore what's in there. We're going to see some function to the power of 5. Some function to the power of 5. So 5 sits in front. Same function to the power of 4. And now the only thing left is g prime of x, class C, n g of x to the power of n minus 1, g prime. So one more time, 5 sits in front. Same thing, whatever it is, to the power of 4. Now the derivative of whatever that g of x, now this requires a quotient rule. So let's multiply by this, the derivative of it, using the quotient rule. Okay, which means the derivative of the top, which is 2 times the bottom, minus the derivative of the bottom, which is 1 times the top, over the bottom square. So take a look. 5 sits in front. Same thing to the power of 4. And now the derivative of the inside, using the quotient rule, and you are done. You are done with calculus. Now your algebraic steps begin. So let's just use a different color to go over that. So this one is 2x minus 16 minus 2x minus 3, 2x and minus 2x cancel each other, you get negative 19, everybody. Negative 19, I hope you see that. So you get negative 19. So let's write it. So we are repeating the first part, and the second part is remaining the same, except the numerator changes to negative 19. And let's see, what happens now? Five is in the numerator. Negative 19 is in the numerator. 2x plus 3 to the power of 4 in the numerator. Notice, on purpose, I cut this into two pieces. One at top, one at the bottom. Each one has the exponent 4, so you see the next step that is coming up. So 5 times negative 19, negative 95, and 2x plus 3 to the power of 4, they belong to the bottom. Now this guy, x minus 8, has exponent 4, and this one has exponent 2. Now 4 and 2, they give us 6. So I hope you see how this thing comes about. It's very simple, class. So just pay attention to it and make sure that you can handle it. I hope you see one step of calculus, several steps of algebra. One step of calculus, several steps of algebra. Okay. You want to differentiate this. Again, the way I approached it last time, I told you I'm going to repeat the same thing. So if I'm differentiating this class, I'm going to ignore that and I'm going to read it in the following format. Cosine, and I'm going to pause. I'm not going to even read the argument. So ignore the argument for now. Cosine, that's all. What does it mean? It means your shell function, the outer function is cosine. So completely ignore that. What is the derivative of cosine? Negative sine. So the answer is negative sine. So let me write this for you. Okay. Okay, let's go into, let's see, let's just, so I'm going to read cosine. The answer is negative sine. I'm going to pause. Okay, the derivative of cosine is negative sine. And I say, okay, now cosine of what? 3t to the power of 4. So I need the same thing for my argument. Okay, the argument of cosine, the argument of sine, they are identical. Okay. Then I say, okay, what about 3t to the power of 4? Well, what is its derivative? By the chain rule, I need that. And now I put that in front, and that's my final answer, class. I put that in front. I hope it's pretty clear as to what's going on here. Okay, everybody? It's really very straightforward. Again, the way I approach it is that I read the outer piece, which is cosine, and I pause, so I know the answer is negative sine. I use the same argument to write my sine now, negative sine 3t to the power of 4. And then the argument 3t to the power of 4 gives me the derivative of 12t cubed. We are done. We are going to move on. Okay, everybody. We want to differentiate those, and we want to see what the answer is. There is nothing brand new. We have seen this when we deal with exponentials. The answer is also always itself. Okay, so if I'm dealing with this, the answer is e to the power of 10x times whatever the derivative of 10x is, which is 10, and I put it in front. Very straightforward. Now, if I'm dealing with this, I say the answer is itself, e to the power of 10x times, now what is the derivative of tangent? Secant squared, and I'm done. Now, whether you put the secant squared x in front or not, it makes no difference. Probably it's better to keep it in this fashion, because if x is sitting next to e, it may be confusing. The only thing I want to make a point of with respect to part C, in case anybody has a problem seeing this, the exponent 2x over 3 means 2/3 x. I just write it this way so you can see when you want to continue with the job what you get. And what you get is very simple. You get itself, e to the power of 2x over 3. And then the derivative of 2/3 x, which is 2/3. And that's why I wrote it in that fashion so that in case you have a hard time seeing the 2/3. Okay, class, I just wanted to make sure we can see that. All right. Now, what do you notice the differences here when we compare these questions to A, B, C? What is the main difference? The main difference that the base is no longer E. So we wonder what happens to it if it's not. So let's figure it out. What happens when the base is different than E? Everybody remember the rules that we learned about logs. If the base is b to the power of x, b is the same as e to the power of ln b. Let me use a different color to remind you of the formula. E to the power of ln x is x. I hope you remember that, class. This is a logarithmic rule. E to the power of ln x is x. So why am I writing it in this fashion? Okay, because remember, we know the derivative when the base is e, but we don't know what the derivative is when the base is no longer e, so we want to see what happens. And what is ln b? ln b is just a number, no more, no less. ln b is just some number, everybody. ln b is some number. So according to the power rule, I can multiply ln b by x. ln b is just some number. So that's why we put it in this fashion. Now, when you look at this one, ln b is the coefficient of x. ln b is like number 7, number 10, number 2, whatever. It's just some number. This, we know how to differentiate. What is the derivative of e to the power of ln bx? Is e to the power of ln bx times ln b. By what? By the chain rule. That we know. So e to the power of ln bx times ln b. Now, what is e to the power of ln bx? Okay. Is the same as b to the power of x. So we put b to the power of x back. What does it mean? It means if the base is different, you still get the same answer, the same derivative, then you need to pay attention to a couple of things. You tag along the ln b. Just for, and we're going to do that in a moment, but for example, 3 to the power of x, the answer is 3 to the power of x, class. So 3 to the power of x is 3 to the power of x times ln b, ln of 3. That's the idea. But what if it gets more complicated? Okay, so 3 to the power of x times ln 3. I hope it's clear to everybody. Okay. What if we end up with this now? B to the power of f of x. Okay. Then again, it's exponential, b to the power of f of x. Okay. Why ln b? The base is not e. Why f prime of x? Because of the chain. Okay. So let's take a look at this last one. Y is 2 to the power of 7x. The answer is 2 to the power of 7x. What is the base? It's not e times ln 2. What is the exponent? It's not x. By the chain rule, the derivative of 7x, or 7. Okay, so the function is itself. The base is different, so ln 2. The exponent you differentiate, you get 7, and you just rewrite it. Now, 7 ln 2, you can put it in the same parentheses. You don't want to leave it like that. It's a little bit awkward, class. This is normally how we write it. And the idea is really to know what's happening. And if you don't put it in a parenthesis, these two, if you don't put it in a parenthesis, these two and these two may be read as 22. So you can put a raised dot in between if you want. In other words, you can say 7 ln2 times 2 to the power of 7x. And that's fine as long as we don't mix things up. I want to make sure that it's done properly. All right, let's move on. If h of x is 4 plus 3 times f of x, where f of 1 is 7, f prime of 1 is 4, and h prime of 1 is 1, okay? We want to find, and we want to find h prime of 1, okay? So never mind h prime of 1, let's find h, okay? Let me use a, never mind h prime of 1, let's find h prime of x, okay? And when we're done, we replace it. So h of x is this, right? Now, how do you differentiate this? Because of the square root, we change it, right, class? Do you remember that? Because of the square root, we're going to rewrite this as 4 plus 3f of x to the power of 1/2. So what is h prime of x? Let's go over it step by step. H prime of x, 1/2 sits in front. You write the same thing and change the exponent to 1/2 minus 1 equals negative 1/2. By the chain rule times the derivative of the inside, the derivative of the brackets, 4 gives you 0, plus 3f gives you f prime of x. I hope everybody's clear as to what happened here. This is the chain rule, everybody. This is the chain rule. And so let's plug in. What do we want? H prime of 1. So replace this one with 1, this one with 1, this one with 1. H prime of x, and now h prime of 1. Okay, everybody? Now let's go and see what we have. F of 1, 7. So this one is 7. 4 plus 3 times 7. Okay. 3 times 7, 21 and 4 is 25. To the power of negative 5, that means take a square root underneath, which becomes 1 over 5. In essence, this is 1 over 5. And 10 times 1/2 is 1 over 10. 3 times f prime of 1. F prime of 1 is replaced with 4. So let's do the replacement, everybody. Let's do the replacement. So 3 and 4, 12 divided by 2, 6. This one goes down, becomes the square root, and this is 25. Remember that? Okay, so the numerator, 3 times 4 cancels out the 2, 6 over square root of 25. 6 over, this is a basic, algebra. Then after that, you just plug in and evaluate. I don't believe anybody has any problem with the evaluation. Okay, so no problem with the evaluation, I hope. And this is pretty straightforward. I hope we are comfortable with this. All right, let's see how we do that. And it's important to go over the methodology that I mentioned. If I want to differentiate this, if it helps, I'm going to rewrite this. I'm looking at part A and part A only. If it helps, I'm going to rewrite it. And I think it does. So I'm going to rewrite it as, okay, cosine to the power of 10. So I want you to ignore this, and I want you to realize, okay, so you're dealing with the extended power rule, something to the power of 10. That's what I want you to see. Do you have to change the format from here to see that? Absolutely not. That's not what I'm saying, okay? But I'm saying, if it helps. Now what happens? Class, 10 sits in front. Same thing to the power of 9. So 10 sits in front. Same thing to the power of 9. Now times the derivative of cosine. So after that, I want to make sure everybody understands that. Then you want the derivative of the inside. Okay. So 10 times the same thing to the power of 9. Now the derivative of the inside. Now, how do you take the derivative? Remember what I told you. The moment I see cosine, I'm going to pause cosine, and I'm not going to say anything else because I want to remember, okay, what is the derivative of cosine? Negative sine. So I need negative sine of this piece, sine x cubed. And then the derivative of sine x cubed. Again, I see sine, I pause and I say, okay, it's cosine, the cosine of x cubed, and then x cubed gives me 3x squared. Now, whether you can see this or not, it has got to do with practice class, okay? So maybe I do this, okay, let me just do this before that. So again, let me just do the writing I erased. So understand you have, let's put an asterisk here, okay? I'm going to replace this with the asterisk. So 10 times the asterisk to the power of 9 times, now I'm going to write d dx of the asterisk. Write this, I think it will be helpful. If you write this one, that would be helpful. Where asterisk is cosine of sine x cubed. Okay. So now the question is, and again, let me write this for you. I want to make sure that you get that. Now, what is this one? Okay, you look at this one and say, okay, cosine, the derivative is sine. Sine of what? The same thing, okay, class? Times, you need the derivative of this. What is this? Sine. So cosine. Cosine of what? X cubed. What is the derivative of x cubed? 3x squared. And now put it back. So now let's go back here. 10 times this thing. So cosine of sine x cubed to the power of 9 times this derivative. This derivative, we did that. Sine, okay. I'm sorry, it's negative. My apologies. I messed it up here. This is minus class. Okay. Minus. The derivative of cosine is minus. Okay. So minus sine of x cubed. And I need to erase this so you can see how that works. So remember, the asterisk is what's inside. I hope that helps. Okay. So, oh, I need to erase this one. All right. So having said that, we just rewrite it. Practically, we are done. Okay. So how do we rewrite that? We put the 3x squared in front, with 10 becomes 30x squared. We put the negative in front, negative 30x squared, cosine x cubed, cosine to the power of sine x cubed, and sine of sine x cubed. Okay. Now, what happens to the next one, class? Again, let's do this. Just ignore this for now. So what do you read? You read this one. Tangent, everybody. What is the derivative of tangent? Secant squared. Okay, again, this is your answer. So the answer is secant squared of this asterisk. Do you see that? So that's the first thing. Now, what is the asterisk? The asterisk is secant of cosine t, okay? Secant of cosine t, and the way you read it is the same thing. Secant of cosine t. So let me write this at top here. Secant of cosine t. So what do you read now? Secant and no more. So what is the derivative of secant? Secant tan. As the derivative of secant is a secant tan. Secant of what? The same argument, cosine t. Tan of what? Tan of cosine t. Finally, the derivative of cosine, which is negative sign. So take a look. Okay. Secant squared of the asterisk. Secant squared of the asterisk. What is the asterisk? Just the argument. Okay. Now times the derivative of inside. The inside is secant of cosine, secant of cosine, secant of cosine. The derivative of secant of cosine is secant tan, secant of cosine, tan of cosine. You see that? And finally, the derivative of in the most inner piece, cosine, is minus sine t. So we are going to rewrite this. They are all in the form of a product. Okay. So negative sign sits in front, negative sign sits in front, and the rest you can put them in any order you want. It's a good practice to put this one in front. Okay, everybody? I want to look at the last problem, which is a word problem. Okay. Now this is as complicated as it gets. This is a page you need to go over a couple of times. If you can do this, you are completely done with the chain rule. You understood it perfectly because this is as difficult as it gets. Okay, class? All right. Could somebody read this question for us, please? Can somebody read it, please?